So till now we have seen uh, two contraptions. One is a common source amplifier, one is a common drain amplifier. Another way of explaining those two contraptions, or another way of uh, going about is going about relating these contraptions with the control sources that we already know, is the following: that a common source amplifier has, so let's say I talk about input impedance and output impedance, right? So a common source amplifier, what is the input impedance that you see in a common source amplifier without taking the source and the load into account? Then input impedance is infinite, right? Or rather I can say it tends to infinite, right? What is the output resistance of a common source amplifier? So let me write it out as common source. What is the output resistance? Output resistance without excluding the load RL, that is looking into the drain of the transistor, the output resistance is also tends to infinite, right? Or in this case it's infinite, right? So among the control sources that you are aware of, what are the control sources that you are aware of? We are aware of voltage controlled current source, voltage controlled voltage source, current controlled current source, and current controlled voltage source. Which of these four do you think a common source amplifier classifies into? Clearly it's a voltage controlled current source, right? This voltage control means input port is infinite impedance, its current source means output port is of infinite impedance. So this falls under the category of VCCS. What is our common drain amplifier? Which category does it fall into? What is Rin? Rin again tends to infinity, right? Because we are looking into the gate of the transistor. One might say it's R1 parallel R2, but I mean that is also in our control. We can say Rin tends to infinity, or if you are not comfortable with infinity, we can say that Rin is high, right? In this case also R out was high, okay, or large. Again, mind you, large, small, high, low, these are all relative quantities. With respect to what? With respect to the load that is attached. Okay, so what about the output impedance in a common drain amplifier? Output impedance is 1 over Gm, which is low, right? With respect to the load, it's low. So input impedance is large, output impedance is small. What do you think this configuration classifies into? I mean, we have talked about this. This clearly is a voltage controlled voltage source with a maximum gain of unity, right? Okay. So now let's so this is ticked off. This is ticked off. Let's try to see if we can attack this. If we can attack current controlled current source. So in a current controlled current source, what do you think the input impedance has to be? In a current controlled, when you say current controlled source, which means the input should be able to take in any current, right? Which means that assumption is that if you have a CCCS, the assumption is that if I have a current source, let's say I have a non-ideal current source. By non-ideal current source, I mean there is an internal resistance. So if I connect this current source to the CCCS block, all of this current I in, let's say in this case I in, should flow into CCCS, right? It is only when the I in flows, it becomes a controlling variable. It's a current is the controlling variable. If nothing flows in, then I mean there's no point in calling a block current control block, because it has to be able to accept current in at its input port, right? So if it accepts the current in the input port in the presence of a non-ideal resistance Rs, what can you comment on the input resistance? Rin has to be Rin has to be close to 0. In this case, Rin has to be 0. It is only when Rin is equal to 0, all of In will flow into the current control current source input port, and no current will flow into Rs. If Rin is not 0, right, then some current division will happen, some portion of the current will flow into the input port and some portion will go into Rs. So in a real current control current source, what do we need to have? We need to have Rin to be much less than Rs. This is real CCCS input impedance. Okay. What about the output side? It's a current source. At the output side, it's a current source, which means output impedance has to be large, like should be infinite, right? So in a current control current source, the input side has to be of low impedance, output side has to be of high impedance. So if that is the scenario, and we would like to make a current control current source using a MOS transistor, right? So what do you think will be our architecture from the perspective of looking into the impedances, right? So a MOS transistor has, as we know it, has three terminals, right? We have gate, drain, and source. Among these three terminals, only two terminals can take in a current input. The current cannot go into the gate, so there's no point in considering that as one of the input terminals for a current controlled current source, right? So which terminal can be used? So I can let's say I have a non-ideal. Let's say I have a non-ideal current source, incremental current source. Let's say In with a resistance, internal resistance Rs, and these are the two ports coming out of the current source. Where do you think should I connect this current source? Should I connect it to the drain? What is the impedance looking in? What I'm essentially asking in this CCCS topology, the looking in terminal, can this be a drain terminal or can this be a source terminal? So what is the looking in impedance into the drain if the transistor is biased in saturation? Looking in impedance is infinity, right? Because it's Y22 at the drain terminal is 0. What is the looking in impedance into the source? What we saw, looking in impedance into the source was 1 over Gm, 1 over the transconductance of the transistor, and by definition we would want the transconductance of the transistors to be as large as possible, which means naturally the impedance looking into the source becomes smaller, right? So if that is the case, where do you think we should connect? We should connect our control source. We should definitely then connect this control, not the control source. Where should we connect this non-ideal current source? We should connect it to the source of the transistor M1. Okay, we should connect it to the source of the transistor, source of M1. But again, you should at this point turn around and tell me that you told me this is an incremental current source. How can I just stick in an incremental current source? And you would be absolutely right. First, we have to establish the transistor is biased in saturation, right? Without the transistor being biased in saturation, nothing can be done. Correct? So, so let's bias the transistor first, right? So let's bias the transistor first, and then we will see what can be done. So let's put it in the side for the time being. So how do I bias a transistor? So let's take our one of our favorite ways of biasing, put a current source at the drain or put a current source at the source. In this case, since I would like to connect the incremental current source to the source cannot be grounded, which means I would like to use the biasing current at the source of the transistor. So this, let's say, is I naught, right? What about the gate? How do we plan to bias the gate? Same old gate. We are not doing anything because we already have established that the input is going to the source. So the gate we can simply bias and leave it. Right. So let's say this is VGQ. Okay. So how do I now how do you propose I connect the input? How do I propose I connect the input to the source? Can I connect can I simply connect the incremental input to the source? I cannot, because now the incremental input has a resistance Rs, and that will load the DC picture, and all those same story will happen. So what is the best way to go about doing it? The best way is basically put a coupling capacitor. Let's call this C2. Okay. What about now the drain terminal? So clearly the drain terminal impedance incrementally is infinite. Y22 is equal to 0 or GDS equal to 0, which means I can take the output from the drain terminal. So in other words, the load has to be connected to the drain terminal. And how do I connect the load? I mean, I can directly connect the load to VDD. Or if you are not satisfied, by now we already know what to do. We can connect this to RD and then AC couple. Let's call this C3, because that's what we were calling it earlier. Connect the load at the AC couple the load like this, and we can take the output across R. Okay. So now what do you think will be what do you think is the input resistance? What will be the input resistance in the incremental model? What do you think will be the input resistance? What is the input terminal? So this clearly is the input terminal. So this is the input terminal. What is the output terminal? So clearly this is the output terminal. Right? So what is the input impedance? What is meant by input impedance? Input impedance is meant by the impedance looking into the input terminal. Incremental impedance looking into the input terminal is what? Again, we have done this multiple times. This is 1 over Gm. Correct? So how much current will flow into the source? Note that in the incremental model, so if you are not if we have to go if we have to sketch out the incremental model, this is what we will see. So in the incremental model, the gate is connected via R1 parallel R2 to ground. This is VG. I have an input which is IN connected to the source of the transistor, Vs. The IN has an internal resistance Rs, and the output is essentially RD parallel RL, and we are taking the output across these terminals, right? And this current is Gm times VGS, correct? What is VG? VG is 0 because it's a floating node. One side is connected to R1, one side is connected to R1 parallel R2. Okay, so VG is 0, so this becomes Gm minus Vs pointing downwards. So this essentially becomes Gm Vs pointing upwards, right? So what is the impedance looking up, looking into the source? The impedance looking in is 1 over Gm. So how much current is flowing into the source? In is appearing at this junction, and it has to decide how much should it go this way, and how much should it go, what portion of it will go into this internal impedance. So how much will go upstairs? So clearly the voltage division of it. So how much? So this will be Rs by Rs plus 1 over Gm will be the current that is flowing through the Gm VGS current source, and this current will flow into the parallel combination of RD parallel RL, and it will create a voltage of so I have to current division, right? So this is minus I in times current that is flowing in, and this current is creating a voltage of RT parallel RL, and this will be the V0. Okay, so in order to ensure that this behaves like a current control source, current control input source, what we need to ensure? We need to ensure 1 over Gm is much less than Rs to realize a CCCS, right? Why are we not bothered about the output side? We are not bothered about the output side because we know the output impedance is anyways infinite looking into the drain. I mean, one might argue that the presence of RT has reduced the output impedance, sure, but I can always increase the value of RT, right, and get things done. Okay, so now here comes a set of terminology again. So again, incrementally, what do you think is happening to the gate? Incrementally, the gate is grounded, right? Input is applied to the source. You are taking the output from the output side, right? So this often is called a common gate amplifier, right? So again, please recall, when I say common gate, what I essentially mean is grounded gate, right? So in this case, the gate is grounded. It's called a common gate amplifier. This is also called a current buffer. Why is this called a current buffer? So in order to appreciate the terminology, so what is a current buffer? So before going into current buffer, what is a voltage buffer? What is a voltage buffer? What is a voltage buffer? A voltage buffer is a contraption that takes in a voltage V1 and produces an output which is proportional to the voltage V1 and is able to drive any load, right? Which means its output impedance is R out is 0, right, and R in is infinite. So what should be a current buffer? What should be a current buffer? A current buffer in plain English should be a contraption that takes in a current at its input side, right? It takes in a current at its input side. So let's say this is the port V1, this is the current I1. It takes in a current at the input side and produces a current at the output side which is proportional to the current that it is taking in, right? So let's call this alpha times I1, and is able to drive any load, which means what? Its output impedance has to be infinity and its input impedance has to be 0. This is an ideal current buffer. And why do we call it a buffer? We call it a buffer because, so let's say I have an non-ideal current source. Let's say I have a non-ideal current source, I in. It has some resistance Rs, and I would like to pass this entire R in through another resistance RL. What is the problem statement? The problem statement is I have this non-ideal current source I in, which has the internal resistance Rs, and I would like to build something here so that the current I in flows into RL. The entirety of I in, or maybe a significant fraction of I in, flows into RL. So if I simply connect these two, what happens? There is a current division that happens, right? And the current that will flow, that is IRL, will be I in times Rs by Rs plus RL. Correct? So now if RL is comparable to Rs, then clearly you see a significant portion of the I in will be lost. And if RL is less than Rs, if RL is more than Rs, then almost nothing of I in will go into RL. Correct? So then we have to put some buffer. So what buffer do we put? We put a current buffer. What is a current buffer again? A current buffer is a contraption that is a short circuit at the input port and creates a current, right? Creates a current which is some alpha times I1 at the output port, and if the RL is connected here, if alpha is equal to 1, for example, clearly the amount of current that will flow here is alpha times I in, which is equal to I in if alpha equal to 1. Right? So the current that flows into RL is independent, it is not dependent on the effect of loading of the RL on the non-ideal current source I in, right? So hence this is the job of a current buffer, to translate the current at one port into the other port without causing any loading. So looks like the buffer that we have, the common gate amplifier that we have, is doing just that, because the amount of current that is flowing in, right? So what is the current that is flowing in? The amount of current that is flowing in is almost equal to I in if Gm times Rs is much greater than 1. Now Rs might not be in your control, but Gm is in your control. You can design your circuit in such a way that Gm times Rs is much greater than 1. If that is true, then almost entire I in flows in regardless of whatever is connected at the output port, right? Since the entire I in flows in regardless of whatever is connected to the output port, this essentially becomes a current buffer, because it is conveying the input current information from a non-ideal source efficiently to the output and isolating the loading effect of the output RL on the non-ideal input source. Okay, so this essentially becomes a current buffer as well. Okay, so what I would next request you to do is to find out what is the swing limits of I in, right? So what I would request you to do is assume I in is equal to some IP sine omega naught t. Find the swing limits of IP, right? Or, or let me say find IP max for which M1 is in saturation and away from cutoff, right? Uh, right. So I hope you will do it before the next lecture, and we'll discuss the answer in the next lecture, right? Okay.